Okay, and this approach is using moment generating functions in order to find the distribution of a random variable. Oftentimes, the random variable is a sum of other random variables. You know, it's pretty commonly used in that type of scenario, and you'll see that as we progress. And so there are some tricks that you may need to make use of. And so that's what is described on the first page of this handout. Some of these you've seen before. For example, when you have two variables that are independent, then you know that the joint distribution is equal to the product of the marginals. I don't remember if it came up, but the expected value of the product is equal to the product of the expected values. That's another one. Then you've got some manipulations. The expected value of the sum is equal to the sum of the expected values. Likewise, the expected value of the difference is equal to the difference of the expected values. And if they're independent, the variance of the sum is equal to the sum of the variances. And so you have those also coming into play. And this, I just saw a typo here. This minus actually shouldn't be there. So even if it's the variance of the difference, that's still going to be the sum of the variance. So that's actually not going to be subtracted. So what else? There's a proof of the moment generating function when y equals a sum. And so if y is a sum of random variables and those random variables are IID, if you've never encountered that, this is independent and identically distributed. That's what IID means. Let me make a quick note here. So this is independent and identically distributed. So IID is a pretty common acronym used for short. So if you have that scenario, so you know all the x's distributions, you know that they're independent, it's the same distribution, and therefore you also know the MGF, or at least you could find the MGF because we've been through that process, whether it's continuous or discrete. Then what you can do is you could derive it like I did here. So let me just walk you through one step at a time. We want the moment generating function of y, which by definition is the expected value of e to the ty. So that's just the basic definition of an MGF. But y is equal to the sum of these x's. So you make that substitution. Rewriting those sum of x's as x1 plus x2 plus x3 plus x4 and so forth, and multiplying through by t, you're just rewriting the power like this. But the exponential of a sum of powers is the same as the product of those exponentials. And so this is just a reformatting. And because all the x's are independent, each of these terms is independent, which means the expected value of this product is the product of the expected values. Now, we know the distribution of each of these x's. So x1 has an MGF of m sub x1, just because that's what was told to us back here. And the expected value of e to the tx2 is the MGF of x2. And likewise, all of them have, the same MGF. And so the product of the MGFs is just the same MGF times itself n times, which is the same thing as the MGF to the nth power. And so this is a general proof that you're going to see applied to a few different specific distributions. So let's go ahead and actually apply it. So you can see it in action. It's not just a proof here. In problem 1, it says an electronic device runs until one of its 3 components fails. The lifetimes in weeks, x1, x2, x3, of these components are independent and identically distributed with the Weibull distribution that is given by the PDF f of x equals 2x over 25 e to the negative x over 5 squared. And so this is a new distribution. It's kind of obscure one, but I'm exposing you to it here. X has the support from 0 to infinity. And we want to know, what is the probability that the device stops working within the first 3 weeks? So that is our challenge here. Any thoughts on how you might begin or attack this problem? Well, I don't see any chat comments. Yep, no, just checking. So let's start setting some things up. So we know that there are 3 devices, x1, x2, x3. And we know that the device fails until it works until one of the 3 components fail. It doesn't matter which one it is. If it's x2 that fails, then the device shuts down. If it's x1 that fails first, then the device shuts down. So it doesn't matter which one ends up failing. We know that x1, x2, x3 are independent and identically distributed. So they all have the same distribution, and that distribution is given as the Weibull distribution. And so all of that information is given to us. There's nothing else that's missing. We also want to know what's the probability that the device stops working within the first 3 weeks. Now the lifetime is in weeks, so that's a quick check. Do we need to make any unit changes? And thankfully we don't. So I'm kind of thinking through, working through what is it that we actually need here. So what I want is to find I need to know the probability that y is less than 3 weeks. So I need to figure out, okay, well, what is y? I'm bringing in this new variable. So y I can view maybe as the minimum of x1, x2, and x3.
Sorry, I don't know that. If you have a minute, I can show you a few things I can do. Do you want to hear more?
No. All right. I guess Alexa thought I was talking to her. All right, so we may want to know what is the minimum time, the minimum lifetime, because x1, x2, x3, they're all lifetimes, so keep that in mind. And so we might define y as, the minimum of these 3. So now what? Well, let's focus on, maybe we could just figure out the probability of one of these failing. It doesn't really matter which one it is. So let's look at.
Wait, did they tell you what y is? You have like y is less than 3.
Well, I defined y, and I said y is the minimum, the shortest time.
Oh,
X1,
so you just
x3 are lifetimes. So they didn't give it. I had to define it, and it's
you
not
could
even
have used any
really
variable.
required. Sorry.
You could have used any variable.
Yep, I could have used W or Q, whatever letter I wanted to. X and Y is really common. I wouldn't have used X because I already have 3 of them. So it probably would have confused me if I had done that. So that would be the only thing, the only recommendation that I have not to do. All right, so I am going to rewrite this as 1 minus the probability that y is greater than 3. So this is that the machine keeps running for more than 3 hours, right? So that's what we're thinking about. And so that means that x1 is greater than 3 and x2 is greater than 3. Whoops, sorry, that should be a greater than sign. And x3 is greater than 3. Because remember, if any one of them is shorter, then it doesn't last for at least 3 hours. So for it to keep running, they each have to still be running. But we know that x1, x2, x3 are all independent. And then you think back to week 1 or 2, and you remember the multiplication rule for independent events. And you realize, okay, well, this is the same as 1 minus the probability that x1 is greater than 3 times the probability that x2 is greater than 3 times the probability that x3 is greater than 3. And so this is by independence. And because they all have the same distribution, I'm just going to use x1 for simplicity. It doesn't matter which one I do. I know all 3 of those probabilities are equal. Again, that is because they are identically distributed. So this is because they are identically distributed. So it didn't matter whether I chose x1, x2, or x3. They're all the same. I just picked x1 because it's first. So now there's really just one probability that I need to find, and that's the probability that x1 is greater than 3. And we have a continuous distribution here. So let's go ahead and figure out that probability. So the probability that x1 is greater than 3 is the integral from 3 to infinity of the distribution of x, which is 2x over 25 e to the negative x over 5 squared. So this is what I want to evaluate. How would you do this one?
Integration by parts.
You could. Does anyone see another path? Integration by parts seems appropriate because you have a product, and you might let u be the x term and dv be the e to the negative x over 5 squared term. But that means you're going to need to integrate dv. Do you know how to integrate e to the negative x squared? I take the silence to mean no. Alvin, I see, and Tony, I see your answer is good. Yeah, so U substitution, Alvin or Tony, what would you let U be? So I have a vote for 1/25, which will make it look a little neater, but there's a better option. So Tony says, let U be the whole exponential term. That won't really help you. It'll probably make it a little uglier. Anyone else have a third or fourth option? So how about U being the power? Whether you include the negative sign or not doesn't actually matter. But you could let U be x/5 squared. Oh, okay, good. I'm glad you corrected yourself, Tony. Yeah, so let's go ahead and do that. So I want U to be x/5 squared, or you could view it as x²/25 just to make sure you don't make a mistake, which means that du is going to be 2x/25, which hopefully you recognize is the coefficient term of this integrand. And there's a dx here, which means that the integral becomes the integral of e to the negative u du. And that is negative e to the negative u, but u is x/5 squared. And we're evaluating from 3 to infinity. This is an improper integral, so I should have converted it into its limit form. I trust that you guys have learned that before. And so as x goes to infinity, the power of the exponential is becoming more and more negative. And so that means that the exponential term is becoming smaller and smaller, or approaching 0. Minus, for when x is 3, we have negative e to the negative, this is 3/5 squared, or 9/25, which is e to the negative 9/25. And now when you go and you plug in here, we've got 1 minus e to the negative 9/25. That term is cubed, sorry, not squared, cubed. And so when you have a power cubed, you multiply it. And so this is 1 minus e to the negative 27/25, which is about 0.6604. All right, so this
Wait,
one,
can you make it?
sorry?
Sorry. Can you make it bigger? I can't see like the whole problem. Sorry, yeah. Isn't it?
This one
You know,
didn't
for the
sorry, just one moment. This one didn't bring into play an MGF. It really had you practice the initial concepts. So, you know, more independence. And I'm just noticing I'm missing a black line here. So there should be an F of X1 there. So it has you, making uses of properties of independence and identical distributions. So MGF didn't come into play in problem 1. Sydney, what's your question?
you know the part where you have a 1 minus, you rule out the 1 minus p of y is like greater than 3. Like I don't understand why you took the complement, like, because like how come you couldn't just go p of everything is less than 3? Because you just like make everything less than 3, right?
Because if you want to stick with the probability that y is less than 3, it's not an and, it's an or. So that would be the probability that x1 is less than 3, or x2 is less than 3, or x3 is less than 3. And there's no independence property that allows you to simplify that statement. But if you want to know that the machine lasts longer than 3, then that means that all 3 components have to last at least that long. And so then it's not or, it's and.
So you have to use and, you said.
Yeah, because and, so this was the multiplication rule of independent events. You had the probability of x, y equals the probability of x times the probability of y. And so you could look back at the probability chapter. I used, I think, A and B, but the same idea holds.
Wait, so you didn't want an or?
Because you can't simplify an or. It's not that it's wrong, it just doesn't help you move forward to get an answer.
You can't simplify.
You cannot simplify an or.
Wait, what do you mean?
What manipulation can you do? What would you do from probably x1 less than 3 or x2 less than 3 or x3 less than 3? What would your next step be?
They're independent, right? So don't you just like
I mean, your silence is good, Sydney, because you should be stuck at this step.
wait, you don't.
You can make use of the general rule. I never gave it to you for 3 events. We have a PA or B equals PA plus BB minus PA and B. But for 3 events, it's going to be longer because you're going to have some additions and subtractions. And so you can do it that way, but it's going to be a lot more complicated.
Wait, so wouldn't it be P A plus P of B plus P of C minus P of A and B and C?
It's not that simple. You could try to do it that way. I mean, not with the formula that you said. You've got pieces there that are appropriate, but it's going to be a lot longer than this approach that I showed. It's good practice though to see if you're able to get at it that way.
So you could do it that way?
But not with the relationship you said. You didn't quite have it right. But you could sketch a Venn diagram with 3 circles that overlap, and then try to figure out what the general probability formula would be for that case. because we had only done for 2 events that overlap, but there is one for 3 events that overlap. All right, let's take a look at 2. So the second problem now tells us that there's a random variable z that is standard normally distributed. I know it's standard normal because it says n 0, 1, so 0 is the mean, 1 is the variance. We want to show that y, which equals z squared, is a chi-squared distribution with 1 degree of freedom. And then once we show that, we want to find the distribution of w, which is the sum of n y's. So, and those y's are independent. Okay, so let's tackle the y equals z squared first. And let's go with the first principles approach. So I'll do this one on the side. So we want the CDF of g of y, which by definition is the probability that y is less than or equal to little y, and y is z squared, which when we solve for y, is the probability that z is between plus or minus root y. And so just sticking with the format that I had done last class, I can tell which distributions each of these probabilities corresponds to. And that final step is with respect to the normal distribution. And so the normal distribution means we want to integrate from negative root y up to positive root y. Let's see, this is 1 over root 2 pi. And you could look at the table of common distributions that I posted. I just happen to know the distribution, e to the negative z squared over 2 dz. So this is what that probability statement is asking for. Now, the normal distribution is symmetric. So that means that this is the same as 2 times half that integral. So I'm going to go from 0 to positive root y. It's not a required step, but it simplifies a little bit. And then this is not an integral that I know how to integrate because it has a z squared power. And so that square, if this was a definite integral with a finite value for y, I could use a numerical approximation, but it isn't. And so I'm going to use, again, that shortcut trick that we learned last class, where I want to take the derivative, so the fundamental theorem of calculus. So the derivative is going to be 2 times the PDF 1 over root 2 pi e to the negative, and now I evaluate z at that y function. So root y squared is y over 2. And I multiply by the derivative of that root y, which is going to be 1 over 2 root y. So I can see that my 1/2 and my 2 cancel out. And that's really all that simplifies, but this is, let's see, 1 over root 2 pi. I'm going to write this as y to the negative 1/2 e to the negative y over 2. And if I put it this way, Now it should really make things stand out, because I know that for chi-square, which is like a gamma form, that theta is 2, and that alpha is r over 2, and r is 1. And so this tells me, therefore, y is distributed chi-square with 1 degree of freedom. And so we did the first part. So again, the first part was just proving that y equals z squared corresponds to a chi-square 1 distribution when z is standard normal. Now the second part is figuring out, well, what's the distribution of w, which is a sum of chi-square random variables that are
Can you
independent.
go back? So what does the 3 dots mean?
Therefore,
Wait, how is that therefore? Like,
it's just a popular math.
oh no, I mean like, I don't understand like why that means, why it proves any.
Because this is, for it to be chi-square, it has to have a gamma distribution where alpha is r over 2 and theta is 2. And so here we have the gamma form where theta is 2, because that's the denominator of the power of the exponential, and alpha is the alpha minus 1 part of the power of y. Alpha is r over 2, and so the numerator is 1. So there's your degrees of freedom.
So 1 is the degrees of freedom.
Mm-hmm.
And then the 2 is alpha,
No, you flipped it.
theta.
Chi-square this is not in the table, so it's just one that you need to know. Chi-square distribution has to have this form. And so for us, we have it in this form now. And so theta is 2, r is 1. And if you wanted to go ahead and prove those coefficients, gamma of 1/2, and it's been a while, but I had given that to you when I introduced the gamma distribution. This is the square root of pi. And then you've got theta to the r over 2, which is 2 to the 1/2, which is square root of 2. And so in your denominator, you have root 2 times root pi, which is the same thing as root 2 pi. And so the proof is in recognizing that this is the very specific chi-square distribution where r is 1. Sydney, can I continue on?
Okay.
All right, so the second part is figuring out the distribution of w, where the w is a sum of n Yeah, n chi-square random variables with 1 degree of freedom. And so over here, now I need to know the distribution of W. And so I'm going to rederive M of W, M sub W of T, which by definition is the expected value of E to the TW, which is the expected value of E to the T times the sum of Y's, which is the expected value of E to the T Y1 times E to the T Y2 times a whole bunch of other E's up to the E to the T Yn. And because they're independent, this is the expected value of E to the T Y1 times all of the other expected values. So the expected value of the products is the product of the expected values. And each of these is an MGF. So this is my1 of t times my2 of t up to myn of t. But because they are identically distributed, this is the same as m of a general y, it doesn't matter which one I pick, up to or to the nth power. So they're all essentially the same, and when you multiply the same thing over and over again, you could take it to that many terms power. So we know what the distribution of y is. And from I think it's here. And from here, we know that the gamma distribution has an MGF of 1 over 1 minus theta t to the alpha. And chi-square is a gamma where theta is 2 and alpha is r over 2, or in our specific case, r is 1. So that means that this is 1 over 1 minus 2t to the 1/2 power to the nth power, which is 1 over 1 minus 2t to the n minus 2 power. And this is an MGF of a very specific gamma distribution. Theta is still 2. What is R now? So R was 1 over here. What's R now? And Miku and Alvin say N, which is correct. So this is now a chi-square distribution. So W is chi-square with n degrees of freedom now. So we know that the square of a standard normal is chi-square with 1 degree of freedom. We know the sum of n chi-square random variables, chi-square 1 degree of freedom random variables is going to be a chi-square n degrees of freedom random variable. And so that's what we just proved using the MGF approach. Tim, I just saw your name. I'm going to give you a shout out though. You got it. Let's take a look at 3. 3 is bringing a few ideas into play. And so in 3, we've got that x1 is Poisson 2 distributed, x2 is Poisson 1, x3 is Poisson 4, and we're told that they're independent. Now it doesn't say identical, because even though they're all Poisson, they have different lambda parameter values. So they're not identical, but they are independent. Y is the sum of these 3 random variables. So we want to generate the MGF of Y. Okay, well, My of T, we know is going to be mx1 of T times mx2 of T times m of x3 of T. No, I didn't write this as an m function to the 3rd power because they're not identically distributed. But if you followed the same derivation that I did in step 2, and even the general one that I did up here, you'll get to this step, which is what I just wrote. And so now I need to know, well, what's the MGF for each of these? And I know the Poisson, I think we even derived it, but rather than guess, let's go ahead and just look at the MGF for the Poisson. It is this last one in the table, so it's e to the lambda e to the t minus 1 power. All right, good. So now we have the MGF. So plugging that in, we have e to the lambda, so mx1, lambda is 2, e to the t minus 1. The second MGF is e to the 1 times e to the t minus 1. And the third one is e to the 4 times e to the t minus 1. Can you simplify this at all? I mean, your answer should be yes. No one has written yes yet. Your answer should be yes. How can you simplify it? What do you get?
You get 7e to the t minus 1.
And yes, so Sydney, you can add your powers, and so you get e to the 7, e to the t minus 1, which means in part B, how is y distributed? It has the MGF of a Poisson. What's your lambda value?
7.
There you go. Yeah, so this MGF approach is really powerful. If excuse me, if it happens to simplify like you're seeing in these examples. And then in part C, you want to compute the probability that y is between 3 and 9 or equal to, so there are equal signs which matter for a discrete distribution. And so over here, you'd want the probability that y is between 3 and 9. And now we know the distribution of y, so this is going to sum up. You've got e to the negative lambda, which is 7, lambda to the y power over y factorial, and y goes from 3 to 9. Of course, you'd use a calculator. Don't try to do this one in your head. And what you should get, which I'll just give you, but you could prove it on the side, is that your answer should be about 0.8. Okay. And so that's going to require a number of these computations, but with a calculator, it's not too bad. But so this is about what you should get for your answer. There's a couple more, or 3 more. So let's take a look at 4. So in 4, you have n x's that are all IID. Remember, independent and identically distributed, and they're all Bernoulli with the same parameters n and p. There's no specific values given for them, but they all have the exact same distribution. We want to show, using MGFs, that y, which is the sum of these n random variables, has a binomial distribution. And so this is something that I said back in the discrete chapter, that the sum of Bernoulli is binomial. And now we're going to prove it. So let's do this. M sub y of t. We know that if we go through all the steps, is going to come out to be m sub x of t. And since they're all identically distributed, all of those m's are going to be the same. And so it's going to be m times m times m times m, n times. So it'll be m to the nth power. Now we need to know what is the MGF for a Bernoulli random variable, which I believe we had found. And so this is your 1 minus p plus pe to the t, or q plus pe to the t, whichever way you want to write that. So this is q plus pe to the t to the nth power. And there's no manipulation that you could do to this. So it doesn't simplify anymore. But remember that q plus pe to the t to the nth power. And if you look here, you have your 1 minus p, which is q plus pe to the t, all to the nth power. And that is the MGF of the binomial. And so that's our proof that this showed that y is binomial NP. And there's actually a typo. So Bernoulli is really only a function of one parameter, which is p. So just cross out that n because it really doesn't matter. But binomial has an n and a p. So that's number 4. So we just proved using MGFs that the sum of Bernoulli will be binomial. In 5, here we've got y is the sum of x1, x2, where x1, x2 correspond to 2 fair 4-sided dice that are rolled. And so it's the sum of the 2 dice. But these are 4-sided. So if you've never played a game like Dungeons and Dragons, you may not have seen a 4-sided die. So just keep in mind that 1, 2, 3, 4 are the only possibilities. We want to determine the distribution of y. So first we need to know, well, what are the distributions of x1 and x2? So they're both going to be the same. So let's look at x1 can be 1, 2, 3, or 4, and because they're fair, all the probabilities are 1/4. And the MGF of x1, by definition, is the expected value of e to the t x1, which is, by definition, the sum of x1 e to the t x1, which, when we now evaluate the summation, we have 1 times e to the t. Sorry, I wrote that wrong. This is just going to be e to the t x1 times the probability of x1. There we go. So this is e to the t times 1. The probability of x1 is 1/4, or the probability of 1 is 1/4, plus when x1 is 2, this is e to the 2t times 1/4, plus e to 3t times 1/4, plus e to the 4t times 1/4. And so that is our MGF of x1. And it's also the MGF of x2 because remember, they are identically distributed. It doesn't say that, but we know that they're both fair die and they're both four-sided. So they're going to have the same distribution and therefore the same MGF. So it's good to recognize that and keep it in mind. Okay, so what does that mean for us? Well, M sub y we know is going to be mx1 times mx2. Which means that we are going to take this and multiply it by itself. So it's arduous, but just do it one step at a time. All right, so when I multiply every term by 1/4 e to the t, and for simplicity, let me factor out a 1/4. And so I'm going to have 1/4 e to the t plus e to 2t plus e to 3t plus e to the 4t times 1/4 e to the t plus e to the 2t plus e to the 3t plus e to the 4t. So that's going to give me 1/16. So that's a common factor across this. I'm just going to multiply the exponential terms and remember to multiply the 1/16 in afterwards. And so when I multiply these exponentials, what do I get? So I get e to the t times e to the t is e to the 2t plus e to the t times e to the 2t is e to the 3t plus e to the 4t plus e to the 5t. And so that is what I get when I multiply e to the t through the entire sum. Plus, now when I multiply e to the 2t through the entire sum, I've got e to 3t, 4t, 5t, and 6t. So that is multiplying the sum by e to the 2t. Continuing, multiplying the sum by e to the 3t gives me and multiplying by e to the 4t gives me that. So now I'm going to simplify by combining like terms. So there's only one e to the 2t, but there's 2 e to the 3t's. Just so I don't lose track, I'm just going to put a mark so I remember what I've actually used. There are 3 e to the 4t's, 1, 2, 3, 4, e to the 5t's. 1, 2, 3, 3e to the 6t's, 2e to the 7t's, and 1e to the 8t. So let me add up the coefficients. I've got 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 3 is 13, plus 2 is 15, plus 1 is 16. So I've got 16 out of 16, which is 1. So I've accounted for every possibility. So all of these were used. All right, but our goal is to determine the distribution of y. So what does this mean? It means that y can have a sum as small as 2 and as high as 8. So 2 when you've got 1 and 1, and 8 when you have 4 and 4. So that makes sense. You didn't actually have to do the MGF in order to know that. But the fact that we got those exponential terms with a 2, 3, 4, 5, 6, 7, and 8, is just confirming that we did that right. And then the corresponding probabilities, well, you have e to the 2t, so that's the sum of 2, has a 1 times 1/16, so this probability is 1/16. The part that's multiplied by the e to 3t is going to be a 2 over 1/16. I'm not going to simplify, I'm just going to keep them like this. 3 over 1/16, or 3 over 16, 4 over 16, 3 over 16, 2 over 16, and 1 over 16. And if you wanted to double check or triple check, you could add up those probabilities to make sure that they equal what value? 1. Thank you, Miko. I was hoping someone would answer really fast. Yeah, so this is our check, and this is our answer. There's only one more problem left. So let's see what we can do with this. Here we have random variables x1 through xn that are all independent chi-square random variables with different degrees of freedom. So that's why it doesn't say identical. They're all chi-square, but x1 is chi-square r1, x2 is chi-square r2, xn is chi-square rn, and so forth. So they have different degrees of freedom. We want to find the distribution of the sum of these random variables. Okay, so I would start off with the fact that we want m sub y of t, which we know is going to be m x1 of t times m x2 of t times all the m's up to m sub xn of t. What would your next step be? Can someone tell me what the MGF of x1 is? If you need to see the table of distributions, just let me know. So hint, in problem 2, we use the MGF of a chi-square 1 inside the first square bracket, or the only square bracket right here. But now we have a chi-square random variable with R1 degrees of freedom. So what changes? That is, yes. So Miku, Alvin, yes, that's correct. So what we should have is this first one is 1 over 1 minus 2t to the R1 over 2. What's the second one? What's the second MGF? And Alvin says change the R1 to an R2. So we've got 1 over 1 minus 2t to the R2 over 2. And that means that the last one is 1 over 1 minus 2t to the Rn over 2. And how does this simplify? What's the power? What do you do with the powers when you have the same base? You add them, right, Miku? And so here you've got R1 plus R2 plus R3 plus R4 up through plus Rn all over 2. So for simplicity, I will just write this as the sum of the Ri's over 2, which means that y is chi-square distributed with degrees of freedom equal to the sum of all of those individual degrees of freedom. So the sum of the Ri's, where I goes from 1 to n. And that's it.
Wait, why do you always have to find the MGF? Because like it's not asking for that.
No, but it's the easiest approach to get at it. If you try to use first principles and get the CDF, you're going to get stuck.
Wait, why
Which
is
worth doing, but it's worth doing to realize that you're stuck, and to recognize that there's probably another approach to use. Because at this point, we've done first principles of getting the CDF and then taking the derivative. We've done the shortcut, which only works if you have monotonicity. We did, for bivariate cases, or even more than 2 variables, the Jacobian. And now you've got an MGF scenario where you have more than 2 variables.
wait, you only do the MGF if it's more than 2 variables?
Well, it's the easiest one if you have more than 2. It works with 2 like we did in problem 5. But it's pretty easy to recognize that typically you use the MGF if you're doing a sum or even subtraction. It's good to be aware of subtraction.
How did you get 1 over 1 minus 2t to the over 2?
How are the x's distributed?
Why are you looking at, do you have to look at the top or
No,
something?
Sydney, answer my question first. How are the x's distributed?
It says independent chi-squared.
Chi-square. And chi-square is a special case of gamma. And so when you go to the table and you look at the third row for gamma, you see the form 1 over 1 minus theta t to the alpha. So then your next step is to say, what is the special case? Well, chi-square is gamma when theta is 2. So that's why I have a 1 minus 2t, and alpha is r over 2, or some degree of freedom over 2. And you're given the degrees of freedom of R1, R2, R3 up through Rn. So that's why the MGFs are those, and that's how we got there.
You know, for the previous problem, where did you get like, okay, so let's find x1 plus x2, and then I don't know where you're getting like that e to the, wait, because originally you had like only up to e to the 4t. I don't know where you got like anything after that, because you had like e to the 6t and e to the 7t, like the next step.
Well, because what I highlighted in yellow is the MGF for just one distribution, but knowing that they're identically distributed, MX1 and MX2 both have that same highlighted yellow MGF. And then in this line here, I know that I need to multiply those two MGFs.
For
And then you
M5.
learned back in, I don't know, junior high or high school that you're going to need to FOIL.
Oh, you just,
Which is what I set up here. And then I actually wrote every term down thereafter. But work it out on your own, and you should see that you get all those terms that I wrote here.
this is e to the t x, right? Did you get that from what it says on the?
Are you asking about this part?
Yeah, like that's on the
That's
top right
the
or something.
definition of an MGF. That you
Yeah.
saw way
Yeah.
back here. That's just the MGF definition. The MGF is the expected value of e to the t random variable, e to the tx, e to the ty. That's where that came from. Does anyone else have questions? I don't see anything on the chat board.
Wait, what was 4?
Okay, I'm not seeing any questions pop up on the chat board. Again, you're welcome to take yourself off of mute and ask them if you do have a question. Winnie, I have a question for you. I know during office hours you had asked about a couple of the web work problems. Do you see how to answer those now? Okay, great. All right, so again, like I said, this is it for the transformation part of the course. And then what we're doing next is just more focused on the statistical side. So if you have experience with statistics, great, you might find some of it easier. If it's new to you, that's fine. I'll be presenting it assuming that you don't have any stat background. But that's where we're moving on to next. And so the chapter topic in my mind, I call estimation, which is a big part of statistics. And so we may not really get into inference, but we'll be doing a lot of estimation, different approaches to estimation. And the first one you'll probably like because it's the easiest. So let's take a look at what's called point estimation, which you've done a little bit, you just didn't necessarily know it. And so in statistics, there's some fundamental concepts that you really need to understand. And one of them is the population, which is the entire group that you're interested in. So the entire group of interest. But for a variety of reasons, it may not be realistic to actually access or talk to or survey that entire group. How many students are at UH Manoa? Is it like the 15,000 range, 20,000, 10,000? I don't actually know. Anyone know? Wow, not a single response. Okay, so I'm just gonna estimate 20,000. I'll throw that number out there. So let's say UH Manoa has 20,000 enrolled students. You know, for a variety of reasons, whether not all of them own a phone, or 13,000 according to Google. Oh, okay, thanks, Sydney. And so we could readjust to 13,000 to make it a little more realistic. And so maybe some don't own a phone or will be difficult to access. Maybe they don't actually live in Hawaii and they're from, you know, international. I think there's a decent international population there. And so it may not be feasible to really communicate with all 13,000 students. And so what you would do is you take some of them, and that group of some is called the sample. Which you could think of as just a subset of the population. But the key point to keep in mind in statistics is that even though we're using samples, we're using just a few, we actually want to learn about the many, about the population. And this is often a hard thing for students to grasp, to say, you know, Dr. Papkov, how can you tell me that the average GPA of UH Manoa students is 3.2 when you only looked at 100 of us? And the reason is because I could tell you that with some amount of confidence. Now, I might be 90% confident that that the average GPA is 3.2. But that means that there is a small part where I could be wrong, the 10%. And usually that detail isn't shared. And so when you hear statistics on the news and they're saying, oh, you know, 56% of people that contract COVID-19 die, I just made that number up, don't freak out. You know, they're not telling you necessarily what that error is. But yet there is some error, there is some confidence associated with that computation. And so, so that's why I'm able to say those things. I'm able to use a small group to say something about the big group. And that's really the focus of statistics. And you're going to get a taste of it for the remaining 2.5, 3 weeks. So let's take a look at this first part. This table summarizes some or most of the popular notation. Some you've seen, some you haven't. So you've seen mu, and you've seen sigma and sigma squared. And those correspond to mean, variance, and standard deviation, but those have to do with the population. And so populations have parameters. So these are population parameters. Whereas the third column here with x bar, s squared, s, and p hat, those have to do with samples. Samples have statistics. Whoop. Notice that P goes with P and S goes with S. I don't really have an easier way of remembering that. So population parameters are estimated by sample statistics. That phrase is really key. Population parameters are estimated by sample statistics. Which means that when you calculate an X bar, that is an estimate of mu. It may be close, it may be far, it really depends on, you know, how much data you have. Obviously, intuitively, the more data you have, the likely it is to be close or closer to the true value. So, and that's just the law of large numbers, which we talked about an aspect of that back in week 1 or 2. So let's practice some of these calculations. And in number 1, it says consider a sample with the values of 1, 2, 3, and 4, and 5. Estimate the mean and the variance of the population. And so this is a sample. We want to estimate mu and sigma squared. Since it's a sample, that means that we're calculating x bar and s squared. So x bar is just the sum of those values. So there's 5 values, 1, 2, 3, 4, 5, which is going to be 15 over 5, which leaves you with a sample mean of 3. So that is our estimate of mu. And then the variance, s squared, I'm going to calculate 2 ways because I want to show you both of the formulas that I list here. So I'm looking at this part. And so using the first one, 1 over n minus 1 times the sum of xi minus x bar squared. So using that, this is going to be 1 over 5 minus 1, because there's n is the number of observations. There's 5 of them, so this is 1/4. And then x minus x bar, xi is your data. So this is 1 minus 5, or sorry, 1 minus 3, your mean is 3. So 1 minus 3 is -2 squared, plus 2 minus 3 is -1 squared, plus 3 minus 3 is 0 squared, plus 4 minus 3 is 1 squared, plus 5 minus 3 is 2 squared. And when you evaluate this, you've got -2 squared is 4, so it's +2 squared, so that's 4, 8, 9, 10, 10 over 4, which is 2.5. And that is your sample variance. So that's using the first summation version. I really only use that version when my x bar is a really simple number, like an integer in this case, and my data are fairly simple numbers. If they aren't, I tend to use that second version of the formula more, just because I feel it's easier for calculation purposes. So I want to demonstrate how to apply this version of the sample variance also. And I'll do that on the side here. And so this is, let's see, we need 1 over 5 minus 1 is 4. And then we need the sum of the squared values. So that's going to be 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9, plus 4 squared is 16, plus 5 squared is 25. If you're not going to remember where that came from, feel free to write down more information. So I know I just said it, did in my head and wrote it, but in your notes, if you're not going to remember where 1, 4, 9, 16, 25 came from, make sure you write 2 squared, 3 squared, and so forth. So these are just the sum of my squared data. Minus, according to the formula, I need to subtract from that n, which is 5, times the square of my mean, which we got to be 3. So this is 3 squared. So this is 1/4. And then 1 plus 4, 9, 16, 25. What's that? That's going to be 10, 20 is 30, 55. Minus 5 times 9 is 45. And so you've got 55 minus 45 is 10 over 4, which gives you the same answer of 2.5. And so that version is my preferred one, just because I think it's easier. And because in my experience, students tend to be more likely to make a mistake with subtracting and then squaring, as opposed to just squaring your data right away. I know that especially students that are dependent on calculators, if you don't use your parentheses and you put in, let's say, -2 squared, it squares the 2, but not the negative sign. So you'll get an answer back of -4. If you are that type of person, make sure you keep that in mind and use parentheses when you are manipulating negative values. Or just think about it, and when you get an answer and you say, I just squared it, should it be negative? No, and so make it positive. Whichever way is going to work for you, just keep that warning in mind. But that is our mean and our variance for problem 1, and that's all that goes into it. And so there's a couple other examples just to practice applying these, because you're going to need to be able to calculate the mean and variance for the future work. So let's take a look at the next one. An experiment was conducted which resulted in the following observations: 1, 2, 1, 3, 4, 4, 5, 5, 9, and 6. So these are another set of nice numbers. We want to use this sample data to estimate the population mean standard deviation. So again, it's sample data, which means we're calculating x bar and s squared. So why don't you go ahead and calculate x bar? And when you feel you've got an answer, feel free to call it out or post it. And I'm going to figure it out on the side. All right, I've got the mean. Again, feel free to post or call out what you get for your sample mean. Start that back up. All right, so a number of you posted on the chat board and you got the answer of 4, which is correct. And so when you add up these values, you should get a sum of 40. And there are 10 values, which means that your average or sample mean is 4. So now, in the second step, you want to get the variance For this one, again, because the data are integer values and your mean is also a nice integer, I'd probably use the first approach that we did in problem 1. And so I'm going to pause the video again and give you a minute or so in order to try to get the sample variance for problem 2. All right, so I see that a few students got to an answer, hopefully more, but at least a couple responded. And so again, this one might be easier using the difference version of the formula, but both would work. Even though I recommended using the difference one, I admit that I used the second one. And so sticking with the difference one, 1 over 10 minus 1 is 1/9. And then you've got 1 minus 4 squared, so -3 squared is 9, plus 2 minus 4 squared is -2 squared is 4. And then 1 minus 4 squared, again, is going to be 9. 3 minus 4 squared.
1 minus.
1. Sorry?
But can you write it out like the minus something squared? Because like, I know there's that equation thing on the top, but I still don't.
Nope, that's 2 minus 4 squared. And that's
Wait,
what.
why does it go back
Yeah,
to
I think
1
that's
minus
what you
4
need.
squared?
Sorry?
Wait, why is it goes to, it says, you said 1 minus 4 squared plus 2 minus 4 squared. It's not 3 minus 4 squared, the next one?
Not according to this list.
Oh, oh yeah, sorry. Okay.
Let's see, 1, 2, 1, 3, 4, 4, then 5 minus 4 squared, 5 minus 4 squared, 9 minus 4 squared, and 6 minus 4 squared. And so we've got 9, 18, 22, 23, 24, 25, 54. 54 over 6, or sorry, 54 over 9. A really ugly 9 equals 6. So this is S squared, but it's asking for the standard deviation, which means S is the square root of 6, which, if you wanted to convert that into decimal form, is about 2.449. And that's your standard deviation. And so what would trick students up on this one is not reporting what the problem's asking for. And so, for example, Tony had submitted an answer of 6, which is on the path to getting the answer, but that's the variance. And the problem's asking for the standard deviation. And so if you forget to check, oh, standard deviation, I have the variance, how do I get it? I need to square root that. That's often the mistake that I'll see for a problem like this. So just make sure that you reread and be sure that you give back what the problem's actually asking for. So problem 3 is along the same lines, compute the sample mean and sample variance of this list of data. Now this one is a collection of uglier values that have decimals, but the process is the same. For a list like this, I'd recommend the variance formula that I highlighted or underlined in red. I think that'll be easier there. And so I'm going to pause the video here and give you time to see if you could do the whole problem on your own. So try to get the mean and the sample variance for this set of 5 values. All right, so some work probably magically appeared, at least showing the solutions or the answers. So I mean, hopefully didn't cause much of an issue for you guys to do. Again, you're just adding up the values divided by the number of values that you added up. It comes out to 7.382 exactly. I recommended and am demonstrating the use of the underlying red version of the sample variance formula, because again, I think in this case and most, it's pretty easy to implement. And so you square your data, add them together, subtract n times the square of the mean. So that's 5 times 7.382 squared. Divide that by n minus 1. 5 minus 1 is 4. And in this case, our sample variance is a pretty small value. It's just 0.45752. So it could be big or bigger, like 2.5 in the first problem, or 6 in the second one, or it could be really small. What the variance represents is an idea of how scattered your data are. So the bigger the value, the more variation or spread there is in your data. For example, in problem 2, you go from values from as low as 1 up to 9. So there's a range of 8. Whereas in problem 3, you only go from a value as low as 6.61 up to 8.36. And so it's just about 1.7 away. So they're closer together, which is why we have a smaller value for our sample variance. And so that's how you can interpret S squared. When you're given one, the bigger it is, the more spread out the observations are, and the smaller it is, it means the closer the values are together. And that's it for just this introduction. I am going to go into the next lesson, but I just wanted to find out if you had any questions about calculating, the sample average, sample mean, or variance or standard deviation. All right, good. All right, so let's actually make use of those and get a little deeper into statistics, because in those problems, we estimated population parameters based on sample information. But like I kind of said earlier, that using a group of 5, 10 observations like we just practiced with, when maybe the population is 1,000 or more, there's probably some error. And so rather than a point estimate, a single value, someone said, well, why can't we come up with an interval estimate or a confidence interval? That's another name for interval estimate, is a confidence interval, which is probably more of what you'll hear. And so now we're going to say, instead of saying that mu is about or approximately 3 in the first case, or mu is about 4 in the second, or about 7.382, now we're going to be able to say that mu is somewhere in the interval of, from 2 to 4 for problem 1, let's say. So let's go and actually see how we could create an interval estimate like this. And I give you the formulas that you would use in this table. And there's 3 scenarios, 2 for if it's mu, population mean that you're estimating, and 1 if it's a proportion. And so let's focus on the mu side first. Which formula you use really depends on what you have. And so if you know the population standard deviation, then you are going to be using the Z table, which is the standard normal table. And that's one you've already seen before. If you don't know sigma, then you're going to be using a different table, which I will introduce probably the next class. And so that's going to be the T table. And so that's going to be your determination. Is the standard deviation or variance that you have that's given in this problem, is that from the population or not? If it's from the population, you're using Z. If it isn't, you're using T. That's really the decision process. So let's take a look at problem 1 here. It says a sample of 10 brand X batteries is obtained and used for a study. The amount of time each battery survived, so its lifetime, is listed in the table below. if the batteries come from a distribution with known variance, sigma squared equals 6.25 hours, determine the 90% confidence interval for the average lifetime of brand X batteries. And so that's our goal, is we want to determine a confidence interval with 90% confidence of brand X batteries. So what do I do? When I look at a problem like this, I first take note, I want a confidence interval for average, which means I'm going to be doing an interval from mu. So then that means I need to choose between one of these first two. So my next question is the variance that I have from the population or not? Is it from the population? Yes, thank you, Miko. It is. That's why it's labeled with the sigma squared. I usually don't put that notation in, but for this problem, it's there. And so since this is sigma squared from the population, that means I'm going to be using the Z star version, which is the first row in the table. So now I know which formula to use. All right, so next, that formula says I need X bar, N, sigma, and Z star. So let's see what I have and what I can get. So X bar, I can get pretty simply by averaging this row. Make sure that you're using the logical row. I say that because I've had students in the past that averaged 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But here we want to know the average lifetime. And the data for lifetime is the second row, 17, 23, 20, 20, 29, and so forth. So make sure you're averaging the correct row. So go ahead and get that average, and I will do it with you, and let me know what you get. And again, when you have a value for the mean, feel free to post. Or
Why is it Z to,
sorry?
why is it Z to X again?
Wait, y is what?
Z to the X?
That's not an X, that's a Z star. Or at least it's supposed to be a Z star. Like an asterisk. So
The Z star population?
of 21, which is right. That's what I got. So if you add up 17 through 15, that second row, you should get 210. And there's 10 values. And so you should get a mean of 21. And I kind of just gave this away. N corresponds to the number of observations in your sample. It's your sample size, which is 10. What else do we need? We also need sigma. Sigma was given. What is sigma? You can calculate it, but it is there. That's right, Miko. Sigma is 2.5. And so I put it into the 2.5 squared version just so you could get at sigma pretty quickly. But if you didn't see it, you could always square root 6.25. And so that's 2.5. And so what we don't have is Z star. But we've actually practiced finding that. And so let me introduce the basic idea behind a confidence interval. And right now, for now, the confidence interval is always perfectly centered about 0. So it's symmetric about 0 for now. And we want to know what are the Z star values. So the same magnitude, just one positive, one negative, that have the confidence level in the middle. And in our case, we are told we want a 90% confidence interval. So that's why I put 0.9 in the middle. What's the total area under a distribution again? 1, that's right. And so if 0.9 is in the middle, how much is not in the center? 0.1, that's right. And so by symmetry, how much is in one side? That's right, half of it. 0.05 is here, and 0.05 is here. So if you add up these three values, 0.9, 0.05 plus 0.05, you get 1. So it's a quick check that you hopefully did things right. And then I would go to our standard normal table. And so pull up, or if you happen to have it printed, feel free to bring that up. And pull up your standard normal table. I'll quickly just pull up a general one. Okay, so here is a standard normal table where these values give the area to the left. So it's similar to the standard normal table that I had provided you guys. And according to our picture, I could look up 0.05 because I know that I'm going to get a Z value corresponding to the area to the left. So I'm going to look for 0.05. And 0.05 is a probability. So I'm making sure I look in the right location. And I see 0.05 is right at essentially the top of my page, close to the middle. There's 0.0505, and the one next to it is 0.0495 essentially. So 0.05 is right in between. The Z-score is negative 1.6 for the first decimal place. And then if I go in between those two probabilities, I see a negative 1.64 and a negative 1.65, which means that the best Z-score is 1.645. And so that's what I've got here, is that this should be negative 1.645, and this will be positive 1.645. So we work backwards. We know the answer, the area, the probability, and we want to find the Z-score. These are called critical values. And critical values are always going to be table lookups. You don't calculate them. So you're not using the Z-score formulas that we used a few chapters back. And so now with the critical values, we have every detail that we need. So using that first formula in the table, we've got X bar is 21 minus a Z star of 1.645 times sigma is 2.5 over the square root of n, which is 10. We know mu is greater than that, but less than. The same thing, but with a plus sign now. And all that's left here is to actually calculate those bounds. So the left side is about 19.7. And the right side is about 22.3. And so there's one last aspect that I would expect you to be able to do other than actually calculate the bounds of an interval like this, and that is to interpret. And so I'm assuming or hoping that all of your parents are not statisticians. And if any of you do have a statistician for a parent, pretend that they aren't. What I want is for you to be able to explain to your parents, what does this mean? And there's 3 parts that I'm looking for. And what I'm looking for is, first, tell me, how confident are you? So we created what I highlighted in yellow on top, which is we are 90% confident. All right, that's the first step. How confident are you? The second step is, tell me what mu means in context. So mu is a mean, but in this case, it's the mean lifetime of battery X or brand X. So we are 90% confident that the mean lifetime of brand X batteries and so that is step 2. How confident are we? What does mu mean in context? And step 3 is to state where we believe that concept is. So what values is it between? So we are 90% confident that the mean lifetime of brand X batteries is between 19.7 and 22.3 hours. So those are 3 phases. How confident are you? What does the parameter mean? And then finally, what is the interval? And every interval or confidence interval that we create is interpreted in this fashion with these 3 components. I've hit my mark, so I'm ending just on time. We're going to continue with this on Thursday, and so at least you got a taste for creating a confidence interval. We'll get more experience, and I'll introduce you to the T-table for the next class too. I'll make sure if I didn't post that I do post one to Lalima. And so with that, I hope you enjoy the rest of your day. I'm going to stop the video here, and I'll hang around for a few more minutes.